All right, so today we are talking about section 8-1, which is the Pythagorean Theorem. One thing I want to make sure you're aware of in this whole chapter that we're going to be doing here the next couple of weeks, dealing with Pythagorean Theorem, dealing with trigonometry like I talked about yesterday, all of that is dealing in right triangles. Okay? In fact, if you look at the Pythagorean Theorem, the actual theorem itself, it says, the very first thing it says, if a triangle is a right triangle. Okay? The Pythagorean theorem only works in right triangles. And the trigonometry we're going to be learning in this chapter, again, is called right triangle trigonometry. We're just kind of scratching the surface on what trigonometry can do for us. All right? If you take pre-calc or calculus, you'll use trigonometry. Obviously, you'll use more trigonometry in the class called trigonometry. If you take a physics class in college, you're going to use trigonometry. Okay? There's a lot that trig can do for us. In this class, we're just going to scratch the surface, learn what the ratios are, and learn about right triangle trigonometry. So I bring that up because this only works in right triangles. A lot of folks try to do this with other types of triangles. It doesn't work. Only in right triangles can we use the Pythagorean theorem. The Pythagorean theorem talks about the side lengths of our triangles. Okay? So a lot of people, whether they know how to use the Pythagorean theorem or not, can spout off that it's a squared plus b squared equals c squared. Okay, a lot of people know that. But what does that mean? What that means actually is leg squared plus leg squared equals hypotenuse squared. Okay? And if you come back to the picture of the triangle, remember that the legs of a right triangle are the two sides of the right triangle that make the right angle. Right? And then the hypotenuse is the side of the right triangle that is opposite the right angle. Now, something else you need to know. The hypotenuse of a right triangle will always be the longest side. Always, 100% of the time. Okay? So, the Pythagorean theorem is comparing side lengths. Leg squared plus leg squared equals hypotenuse squared. And the hypotenuse is always the longest side. Something else you need to know. We have the two legs here. It doesn't matter which number you plug in for which leg. Okay? Which value is A versus which value is B, that doesn't matter. The one thing that does matter in the Pythagorean theorem is which value you're plugging in for the hypotenuse. C always has to be the hypotenuse. C is always the longest side. The two legs doesn't matter which one's A, which one's B. But C has to be a specific value. All right, so let's give it a shot. Let's see what happens here. I think you guys have seen the Pythagorean theorem before. If not, this will be a good refresher for you. So we want to find out what is the length of the hypotenuse of triangle ABC. So looking here, they've already told us we're looking for the hypotenuse, but also looking at the diagram, notice that 20 and 21, those two sides form the right angle, right? And so therefore, those must be the legs of our right triangle. So I'm going to write down the Pythagorean theorem. A squared plus b squared equals c squared. And A and B are supposed to be the legs. So does it matter which A or B I plug in 20? No. I can plug 20 in for A or 20 in for B. Doesn't matter. It's leg squared plus leg squared equals hypotenuse, which, by the way, the hypotenuse is line segment AB. I'm going to write it that way. Again, that's a refresher from first semester. A and B are referring to points, A and B. And then if I write AB together without any symbol on the top, I'm talking about the distance from A to B. All right, so AB is the distance from A to B. That is a number. So at this stage, we can use our calculators. You probably know 20 squared already. Yeah, 20 squared is 400. What is 21 squared? 441. And that's going to equal A times B squared. I'm sorry, AB squared, not A times B. Shame on me. AB squared. So 400 plus 441 is 841. And so now how are we going to solve for the length of AB? We saw this yesterday. Yesterday, I wrote on the board x squared equals 25. And I told you guys, hey, remember in Algebra 1 where we're going to take the square root of both sides and we're going to get x equals 5, right? Everybody said, uh-huh. How are we going to solve for the length of AB? Take the square root of both sides. We've got to get rid of the squared. So to get rid of that squared, we have to take the square root of both sides. And so then AB equals what?
29.
29. AB equals 29. That is the length of our hypotenuse. So that's how we use the Pythagorean theorem. The key on the Pythagorean theorem is making sure that you're plugging in the proper length for the hypotenuse. Now in this particular problem, we were looking for the hypotenuse, okay? Sometimes you're going to know the hypotenuse and you're going to know one of the legs, and you then need to solve for that missing leg. All right, but it's a matter of plugging in properly and then using your algebra skills to solve for your missing length. This particular problem, these lengths, 20, 21, and 29, are referred to as a Pythagorean triple. A Pythagorean triple. What a Pythagorean triple is are three whole numbers that work in the Pythagorean theorem. Okay? Three whole numbers that work in the Pythagorean theorem. So let's go up here in our notes where we talk about Pythagorean triples. So, a Pythagorean triple is a set of non-zero whole numbers, a, b, and c, that satisfy the Pythagorean theorem. We have four of them here that we use in this class often. It would be wonderful if you memorize all four of these triples. But if you don't memorize them all, I would at least like you to memorize the first one. At a bare minimum, memorize the 3, 4, 5. Not only will that help you in this class, but that 3, 4, 5 right triangle shows up in the ACT, it shows up in your trigonometry class, it shows up in your pre-calc and calculus class, it shows up in physics classes, it shows up all over the place. Okay? The 3, 4, 5 Pythagorean triple is a handy one to know. What does it mean? What it means is that if I have a right triangle where one side length is 3 and one leg is 3 and one leg is 4, then I know the hypotenuse is going to be 5. Okay? And we can prove that to ourselves by plugging it into the Pythagorean theorem. 3 squared plus 4 squared is supposed to equal 5 squared. 3 squared is 9. 4 squared is 16, 5 squared is 25. And sure enough, 9 plus 16 does equal 25. Okay? So that's what these Pythagorean triples are. They're three numbers that work in the Pythagorean theorem. One thing to notice though, like I said before, the hypotenuse is always the longest side. So when you look at these Pythagorean triples, 5 has to be the hypotenuse. 13 has to be the hypotenuse. 17 has to be the hypotenuse. And 25 has to be the hypotenuse. Okay? That's the only way they work. Why am I bringing this up? Well, if I had a triangle where I had this is 13 and this length is 5, and I'm solving for x, I can then notice that, all right, I've got a hypotenuse of 13. That I recognize as being part of a Pythagorean triple. A leg of 5, hey, that's also part of that Pythagorean triple. Therefore, my other leg must be 12. I'm done with that problem. There's nothing more I need to do, no more work I have to show. That's it. It's a Pythagorean triple. But what if I have a triangle that has, this is 17 and this is 8. And I'm trying to solve for the hypotenuse. Don't fall into the trap of seeing, oh, 17 and 8, that's part of a Pythagorean triple. The hypotenuse must be 15. Problem with that, the hypotenuse has to be the longest side. Therefore, in this problem, you cannot use Pythagorean triples. I'm not saying you can't solve this problem. I'm just saying that that problem can't be solved using Pythagorean triples. Okay? In that particular problem, you would have to plug into the Pythagorean theorem and work it out. So, Pythagorean triples are 3 sets of whole numbers that work in the Pythagorean theorem. They're handy to have. Why? I said at least remember the 3, 4, 5. Why? Well, let's take a look at this next problem right below. It says the legs of a right triangle have length 10 and 24. What is the length of the hypotenuse? In my opinion, always draw a picture. It just makes life so much easier. You don't have to make it exactly to scale. It doesn't have to be a great picture. Just draw a little sketch so you can visualize what's going on. Okay? We're talking about the legs. Legs are the sides that form my right angle. So that means 10 and 24 must go there. Okay? And it doesn't matter where you put the 10, where you put the 24. That's not important. We are trying to solve for the hypotenuse. Now, yes, we could plug into the Pythagorean theorem. You could say 10 squared plus 24 squared equals x squared and solve it. Okay? But that is going to take more time than if you notice that this is a 5, 12, 13 Pythagorean triple. Okay? You might be saying, well, why is it 5, 12, 13? It says 10 and 24. 10 is 2 times 5. 24 is 2 times 12. Those are part of my Pythagorean triple, 5, 12, 13. So that means my value of x must be 2 times 13. Okay? The Pythagorean triples work when there are the multiples of those triples, meaning 3 times the Pythagorean triple, or 4 times the Pythagorean triple, or even something crazy like the square root of 2 times the Pythagorean triple. Okay? So those Pythagorean triples will work even if we're talking about multiples of those. Why? Think back to when we worked with similarity. All we're doing is taking that triangle, keeping its angles the same, but making it 2 times bigger, or making it 3 times bigger. It's still the same triangle in essence. It's still similar to that. It's just bigger than the original. Okay? So 26 is the hypotenuse. Questions? No. Okay. Well, let's do another problem. Let's take a look at this one here. We're trying to find the value of x. Now, something I want to show you goes along with that idea of multiples of the Pythagorean triples. You can use that idea of multiples in other places as well, just to make your life a little easier. Because if I use 20 and 8 in the Pythagorean theorem, it can be done, but I work with bigger numbers, and then I have to reduce down my radical. We can work that after we do this if you want. What I would like to see you guys do is work that idea of multiples, meaning 20 and 8 have a common multiple, or a common factor, excuse me. What number goes into both 8 and 20? 4. 20 is 4 times 5. 8 is 4 times 2. Therefore, x, the value we're looking for, has to equal 4 times some other number. I don't know what that other number is. Don't call it x. Let's call it y. Okay, because you don't want to get confused on which variable you're solving for and which one you found. Okay? So, we're solving for x, that entire length, but we know that x is going to equal 4 times y. We don't know what y is, but I do know that I can use 2, 5, and y in the Pythagorean theorem. It's not a Pythagorean triple, because 5 is not a hypotenuse. 5 is the hypotenuse, but 2 is not one of the legs of that triangle, that triple. But I can use 5, 2, and y. Y squared plus 2 squared equals my hypotenuse 5 squared. Y squared plus 4 equals 25. I've got to subtract 4 from both sides. Y squared equals 21. How am I going to solve for y? Not square it, square root it. Square root it on both sides. So then y equals the square root of 21. Technically, I should get two answers. Technically, I get a positive and a negative answer because I put the square root in there. But can I use the negative answer here? No, because I'm looking for a length. I'm looking for a distance. And so y equals the square root of 21. That is not my answer. X, what I'm solving for, is 4 times the square root of 21. That's really the difficult part of doing it this way, is remembering to write that multiple out in front when you find that answer. Okay? So what would happen? What if you say, all right, well, Mr. Bobier, what you just did is crazy confusing. I just want to plug into the Pythagorean theorem. Okay, that can be done. We had x squared plus the other side length there was 8. The other leg was 8 squared, and our hypotenuse was 20. So x squared plus 8 squared equals 20 squared. And now we work that out. Well, what is 8 squared? 64. What's 20 squared? 400. And so what I need to do now is take 400 minus 64. A couple of you with calculators in here. What do we get? $336. All right, cool. Now I've got to solve for x. I'm going to take the square root of both sides. And so if you take the square root of 336, that does not come out to be a nice perfect square. So that means we have to reduce it. All right, so I got to have my list of perfect squares here. So 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, so on and so forth. What is half of 336? 168. So that falls right there. That means we've got to try all of those perfect squares. So what we do, you can call me Mr. Bobier, it's fine. So what we do is we take 336 divided by 144. All right, does that work? Punching buttons? No. We take 336 divided by 121. Does that work? You said no before I saw you punch it in. Oh, there he goes. Okay. No, it doesn't work. I'm going to save us a little time here, guys. Doesn't work, 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 doesn't work. Oh, that one works. How many times? Oh, 21. Okay. So this is the square root of 16 times 21, which is the square root of 16 times the square root of 21, which is 4 square root of 21. Cool. Now we fast forwarded our work there a little bit. Let's add on an extra 2 minutes for punching buttons and checking answers. Okay? That process, it works. It's perfect. Gives us the same answer as what I did with the multiples. The multiples didn't require a calculator. It didn't require me go through that whole process of reducing the radical. Okay? So it is, in essence, faster. But you got to practice it if you want that to be a valuable method for you on a test or a quiz. Okay? Questions? No? Let's stop there, give you some time to work on homework.